For the Cauchy Euler equation, that's another form of the equation. And the way to solve similar way as getting YC and YP. But the process is a little bit different. So for the Cauchy Euler equation, okay, it's in the form for the n order. You have the coefficient multiplied by x to the n for the order n, coefficient multiplied by x to the n minus 1 for the order n minus 1, x to the and multiplied by the first order. So that's the difference of the Cauchy Euler equation and the constant coefficient equation for the 4, 3, 4, 4, and the one that we just saw in 4.6. For the second order, as you see, the coefficient A is a constant, but the typical form is second power of the x with the second order, first power of the x with the first order, and no x for the zero order. Okay, so this is the pattern or the form of the second order Cauchy Euler equation. Okay, A will not be zero, otherwise you don't have the second order to work on. So with this one, when you increase the order, you have more power of the x. So then for the when you add together, if the right hand side is one form of the function, and if we look at the solution for the non-homogeneous, we always started with the associated homogeneous equation. So for the associated homogeneous equation, the right-hand side is zero. So think about the function or the solution form. That's when you keep doing the derivative and it keeps returning in some sort of the power involving it. So then the trial solution or the guess or the educated guess solution would be in the form of y equals x to the power m, or the power function as a solution form of the Euler or Cauchy Euler equation. Then with this, like for the constant coefficient equation, the trial solution will be in the form of the e to the power, right? Because when you find the derivative, you have the same form of the exponential, but the thing that change is the coefficient as a constant. The constant changing depends on the power of the e. But this one, when you have the power, every time you do the derivative, the power is reduced, reduced, reduced. And if you do the first power, the power is reduced by 1. You multiply 1 power back in, you get the same form as the original. So that's the concept of coming up with the solution of the Cauchy Euler solution. Okay. So from the pattern here, if y equals x to the m as a solution, the first derivative gonna be m x to the m minus 1. Second derivative gonna be m, keep multiplying with the current power, right? M minus 1, x to the m minus 2. And if you keep going again, it's gonna be m minus 1, m minus 2, x to the power, this is m minus 3, and so forth. Okay, so the coefficient will change based on the current power of the x. So when you put them together, second order with the coefficient a, so this is the derivative, the second derivative of the solution form, the first derivative of the solution, and this is the solution form. So if you multiply the first derivative by x, second derivative by x squared, you're gonna have the common power for the x for all terms, and then factor that one out, then you get the equation in the form of a, which is the coefficient of the second order, times m minus 1, plus b, or the coefficient of the first order, times m, plus c, which is the coefficient of the zero order. And this equation is called the auxiliary equation for the Cauchy Euler equation. And the m is the power that we consider m should be some number that we can find out from solving this equation, And with the zero product property, x to the power m should not be zero. Otherwise, If x is 0, what happens? Is trivial solution, nothing to do with that. Okay, so to work on the x auxiliary equation, which is the a coefficient m minus 1 for the second order plus b times m and then plus c equals 0, we're going to use this equation to solve for m1 and m2. And again, this is the power 2 or the degree 2 equation, which is the quadratic equation. You can use the quadratic formula to solve for m1 and m2, and then the solution will fall into one of three cases, similar to the undetermined coefficient, similar to the way that we did in 4.3 about the solution of the constant coefficient form. For the distinct roots, like m1 and m2 are not the same. Now you're gonna put solution in a form of c1 times y1, c2 times y2, where y1 is x to the power m1 and y2 is x to the power m2, and yc is c1 times y1 plus c2 times y2. Recall, like the trial solution form is x to the power m. So we're gonna use m as the power of the x, not the power of the e, like the constant coefficient. For the repeated real roots, m1 equals m2. Yes, the y1 gonna be x to the power m1, but y2, it cannot be the same as y1 because we have to make it as the linearly independent from each other. From 4.2, that y2 can be found using the reduction of order formula, like u times the y1 solution, and u is the function. So section 4.2, the reduction order, will come out as a solution in the form of the second solution will be multiplied by natural log x on top of it. So if you have y1, or y1 is already known from the pattern of the solution, y2, you keep the same x to the power m1, but you multiply on top of it with the natural log x, which is different than the constant coefficient that you keep multiplying by the power of the x, right? But this one you keep multiplying by the natural log x term. So in the case you have three solutions, like m1 equals m2 equals m3. So y1 is x to the m1. Let me write it as a m. So y1 is x to the m. y2 is the same x to the m, but multiplied by log x. And y3 is going to be similar way, but you keep multiplying by another log x. Or we can say y3 is x to the m multiplied by log x to the power second. So you keep multiplying by another log x when you have another repeated solution. That's the solution for the case to repeated real roots. And then for the conjugate complex, you're going to use the real part. So this in the form of alpha plus minus beta I, right? The alpha is the power of the x, nothing to do with the e, okay? This is about the pattern x to the power m. And then the beta, which is the imaginary part, will be part of the argument of the sine cosine. So going to be beta times log x, beta times log x. You can see natural log x come in similar way that you multiply x into the pattern of the solution, but this time going to be natural log x everywhere, okay? Instead of exponential, we're going to have the x to the power of the term instead. So three cases of the solution. All right, let's see the first example. The first one here, we have the differential equation in the form of x squared y double prime plus 5x y prime plus 3y. You can see this is the second order, second power, first order, first power. We have a equals, a is a coefficient of the highest power, a is 1, b is 5, and c is 3. And this is the homogeneous Cauchy Euler equation. Okay, to find the solution, it's going to be solution yc. The auxiliary equation is from the a times m minus 1 plus b times m plus c equals 0, because it's from, like, if your solution y equals x to the m, y prime is m x to the m minus 1, y double prime is m times m minus 1 x m minus 2 power. So you can see the second order, you have coefficient m, m minus 1. First order, you have m. Okay, this is the setup to find the solution. So A is 1 times m minus 1, and B is 5, so 5 times m, and then plus C, which is 3, equals 0. You have the equation power 2, or the quadratic equation. What you would do after this, expand it a little bit to see the normal quadratic equation. So we have m squared minus m plus 5m plus 3 equals 0, or m squared plus 4m plus 3 equals 0. Okay, factor, we have m plus 3 times m plus 1 equals 0. Then 2m's, m equals negative 3 or m equals negative 1. We have case 1, which is the distinct real roots. When you have these two, did I get the right number? Negative 3, negative 1, yes. And then from each m, you put together as a solution. So y1 is x to the power negative 3. y2 is x to the power negative first. Therefore, the solution, which is c1 y1 plus c2 y2, is in the form of c1 x to the negative third plus c2 x to the negative first. Oops, where did it go? Again, this is a problem when I use the word, the x to the negative 1 as a solution, or the general solution for this homogeneous Cauchy Euler equation. Question is tedious in different way. The difference is the setup of the auxiliary equation. All right, let's see the second example. The second example here, again, Cauchy Euler homogeneous, second order, second power, first order, first power. The A is 1, the B is negative 1, C is 1. Okay, the auxiliary equation is 1 times m minus 1. First, the b, which is negative 1, times m, and then plus c equals 0. So a here, b here, and then c here. And then we're going to solve the m similar as the last example, similar to the last example. So we have m squared minus m minus m. Oh, c is 1, sorry, this is 1, and then plus 1 equals 0, equals 0. Or m squared minus 2m plus 1 equals 0. Okay, looks like we have repeated solution. M minus 1 equals 0. So m equals 1, m equals 1. The way that I wrote it as two factors, just to remind myself that I'm going to have the two solutions. And if I wrote it as m equals 1, I would mislead myself to have only one solution for the problem. Okay, so this is my recommendation. Oh, where did it go? Oh, not yet. Okay, there you go. So my recommendation, when you have the power 2, write out all factors, even though you see the common factors. So you have m1 with the same m value. So this is case 2, or the repeated solution form. So my y1 is x to the power 1. My y2 should be the same, x to the first power. It's repeated. Every time you repeat, you multiply by natural log x. Then the y equals c1 y1 plus c2 y2, or c1 times x plus c2 times x times natural log x as a general solution.